Good morning, good afternoon, and good evening. My name is Harry Lee, and today we're going to derive Navier-Stokes equation as well as understanding its mechanism. So this is right below here is the Navier-Stokes equation, which is also known as one of the hardest mathematical differential equations. And this is also part of the millennium question where you get $1 million when you prove or solve this equation. So actually, there's no specific proof to this equation, but we still have the closest estimate of this equation and we can derive this easily. So here's the Navier-Stokes equation, and you might wonder what exactly is this long, really unknown variables and everything. So Navier-Stokes equation is just another way of writing Newton's second law, which is F equals to ma. So mass times acceleration equals to sum of the different forces that are exerted on a particle. So in this case, let's say that there's a fluid particle, gas or liquid, and there will be different forces that apply to that specific particle, and we can get the sum of those forces and say that they are equal to the density times the acceleration. The reason why we're using density instead of mass is because in fluid mechanics, the particles are fluid, so they cannot really have a specific mass values. That's why we need to divide them by the specific volume, which is m divided by volume equals to density rho. That's why you can see that this rho part density refers to the mass, and this long differential equation refers to the acceleration. So let's first derive the left side of the Navier-Stokes equation. So you can see that the left side is rho times partial v partial t plus this velocity and the gradient combination refers to the acceleration. So how to get these? So this is easy. Actually, the first part, rho, is just mass. So that's just straightforward. But this acceleration part is a derivative of a velocity function. So when you learn in the calculus, we learned that dv dt equals to acceleration, right? But it doesn't work that simply in a fluid mechanics. The reason behind is because velocity has multi-variables. So in a fluid mechanics, velocity has x, y, and z directions with respect to time. So when there's a fluid particle, it has its own velocities in the x, y, and z directions, and it changes over time. That's why we have four different variables for the velocity, and when we take the derivative of this velocity function, it's not going to be simple as just dv dt equals to a. So in a multivar, we learned that whenever we take a derivative of a multi-variable function, let's say that there exists a function called f x y. So it has two different variables, and when we want to take a derivative of this with respect to a new variable called t, then this equals to partial f partial t plus partial f partial x times partial x partial t plus partial f partial y times partial y partial t, so that the partial x's and partial y's can eliminate each other, and we get these, which also equals to dv dt. So when we take a derivative of this velocity function with x, y, and z and t variables, it will equal to partial it'll be partial v in this case, is because it's velocity, partial v partial t plus partial v partial x partial t plus partial v partial y last but not least, partial z, partial t. So this is the full derivation of a velocity function with respect to t, but it also, you can see that it also contains x, y, and z variables inside there. So technically this part is this part. But this part is just a simplification of this, because we know that partial x, partial t in fluid mechanics is just u. And partial y, partial t is v. Partial z, partial t is w. And you can see that we can rewrite this equation in terms of partial v, partial t plus partial x times velocity times u plus partial y times velocity times v plus partial z times velocity times w. So we can rewrite this in terms of the gradient vector because it contains partial x, partial y, and partial z. And you can see that for each variable, the velocity function is added, right? So it will look like gradient vector is velocity. But you also need to know that we have the u, v, w, which are velocities in x, y, and z directions. So therefore, we have to multiply v, which is velocity, one more time, and just add the partial t, 1 plus. So there we go. So we first got the left side of the equation, which is just Newton's second law, ma, which is rho times partial v, partial t plus the gradient times velocity vector, and those product multiply the velocity one more time, which refers to the acceleration. Now let's start with deriving the right side of the equation. And before then, we first need to know the three different forces that exist in a fluid mechanics. So there are three different types of forces in fluid mechanics, which are gravitational force, pressure, and viscosity. And when we find a force in the Navier-Stokes equation, we cannot just find the F, right, which is force. The reason why is because the fluid particle in a fluid mechanics is so small so that we can't really get the value of the F directly. Therefore, the scientists have promised to find the dF dV, which is the change in force per unit volume, which is the most accurate way of finding the force that is exerted on a particle. So we need to find dF dV for the next three forces, where each part refers to different types of forces. So the number one, this part is gravitational, this one is pressure, and this one is viscosity. So let's first start with the gravitational force. So in order to find the gravitational force in the Navier-Stokes equation, we just literally have to find the specific weight that is applied to the particle, right? The reason why is because when we derive the equation, we know that specific weight equals to weight divided by volume. So weight divided by volume equals to gamma. So gamma is the symbol for the specific weight. And we know that the dV gamma equals to mg, and therefore the gamma dV, putting on the other side, equals to dF. And what did I say? We need to find the change in the force per unit volume. So dF dV equals to gamma. So we just have to find the gamma and we can call it a day. So what is gamma? So we know that weight W equals to mg. So mass is very objective measurement of the mass. So mass is the objective measurement, but weight really depends on the different gravitational forces. Like on Earth, we apply a 9.8 gravitational force, but on the Mars, it's really different. So weight is subjective and mass is objective. So we know that weight equals to mg, right? But what is gamma? Gamma equals to weight divided by volume, which also equals to mg divided by volume. And what did we say before? What is mass divided by volume? Exactly. This is density. Rho. So gamma equals to m divided by v times gravitational, which also equals to rho g. So here we go. We finished the first part of the Navier-Stokes, which was very easy peasy. It's literally just rho g, which is the gravitational that is exerted on a particle. Right, so let's move on to the second part of the Navier-Stokes equation, which is pressure. So pressure is any force that involves any stretch or compression. So in order to understand and derive the pressure that is applied to a fluid particle in Navier-Stokes equation, we need to know the Taylor expansion. So in a multivar, we learned that Taylor expansion is another way of writing the easy y equals to mx plus b, which is using the slope and plugging in the values such as the difference of the values of the x variables in order to find a new point in a Cartesian coordinate system. So we know that in the Taylor expansion, the fx equals to the original point plus the first derivative, which is also known as the slope, and we multiply the dx. So in Navier-Stokes equation, we can go this far for the accuracy, but in this part of the video, we're only going to use the first part. And what is this? This literally equals to y equals to mx plus the z's equation. So let's first look at this. So we know that force equals to pressure times area. So let's say that there is a pressure that is applied on this side of the equation of this particle. Then we know that the pressure is P. Then the pressure force that is applied on the other side of this particle will be, using the Taylor expansion, it will be negative because it's on the other side of P, which is the original pressure, plus partial P, partial X, dx. The reason why we're deriving this with respect to x is because this is on the x side, so of the x. And we need to get the y sides and the z directions as well on the multiple sides. And we, at the end, don't forget to multiply this by dy dz. Why? Because this one is the area of this rectangle. So when we just continue this for the next y and the z directions, we get, so let's rewrite the x1 as well. So on the x, we have p x dy dz minus px dy dz. And for the y direction, it will be py. This time it will be dx dz minus the pressure y plus partial p partial y dy times dx dz. For the z direction, it will be pressure on the z side. This time it will be dx dy minus this is it. So when we have these summations, we know that since there is a negative sign for each x, y, and z directions, we know that these cancel out. They all cancel out, and we are left with negative plus times dx dy dz. And we know that dx dy dz, what is x, y, z? We know that this is volume, so thus this can be rewritten as dv, which is volume. And what did we say this can be rewritten as? Exactly, the gradient vector. So this equals to minus gradient p dv. So we know that df equals to this equation that we derived on the right side. But what did I say before? We need to find change in the force per unit volume, df dv. So this equals to this, which is exactly the right side of the Navier-Stokes equation. And we're done with the pressure part. Alright, the last part of the force of the Navier-Stokes equation is the viscosity. So what is viscosity? Just think of the honey. When you look at the honey, it is very sticky, and you know that it's like a stress or a tension or force that changes its shape and the movement of its object, something like honey, right? So we need to know the concept of tensor. So tensor is whenever a 3D object that explains a multi-linear relationships that are applied on a object. So in physics, we learned that like the scalar is just like a value, and the vector is the on the 2D. Tensor is a value of any kind of forces in 3D object. So what kind of force that we are looking at? The stress, because stress is the key point of the viscosity, and it's what it makes like honey really sticky. But there are two types of stresses that are really important. One is a shear stress, and another one is a normal stress. And from its name, you can infer that the shear stress is very parallel. The stress is very tangent to the surface, and the normal stress is perpendicular to the surface area. And the notation for the shear stress is tau, and the notation for the sigma is the notation for the normal stress is sigma. And the scientists and the mathematicians have promised to denote any kind of stresses in this way, where tau xy refers to the stress on the x-plane at y direction. So this part refers to the plane of the particle and the stress, and this one right here is the direction of the stress. And let's say that there is a particle right here, the square, and in this cube, there are multiple tensor and the stresses that we can write. So we need to draw 3 cubes. So I'll copy and paste. Okay, so let's look at the top side. It will have 3 because each plane will have 3 different stresses. 2 shear in the xy direction and 1 normal, which is the z direction. So look like this. And above here will be sigma yy. On the right side, it will be tau yx. Here will be tau yz. On the second cube, let's write the shear stresses on this side of the plane. In this case, this one will be tau xy. This one will be tau xz, and this will be sigma xx. Because they're on the x plane. Last but not least, let's look at the z sides. It will be this, this, and this. And this one will be tau zy, will be tau zx, and those will be sigma z z. So we wrote the shear stresses on each side and set that as like a default value. What we have to do here is that we need to reuse the Taylor expansion to write the shear stresses on the opposite sides of this cube. So for the y direction, it will be this side. For the x, it will be this side of the cube, and for the z side, it will be this. So rewriting those, and this part is, by the way, the hardest part. So just skip it up. So we know that. Let's first start with the, I think it's most appropriate to start with the x plane. So we need to write the shear stresses in 3 directions. Starting with the x will be sigma xx dy dz minus sigma xx plus partial sigma xx x dx dy dz. So this one will be tau yx dx dz minus tau yx plus partial tau yx with respect to y dy dx dz. And this one will be dx dy minus tau zx plus partial tau zx respect to partial z dz dx dy. So we got the first one, and we need to do the same thing for the y and the z directions. This one will be minus tau xy plus partial tau xy partial x dx dy dz. This one will be this minus sigma yy plus dx dz. This one will be minus tau zy plus partial tau zy be partial z dz dx dy. Alright, last but not least, let's do the z direction as well. I feel like in order to become like the really great mathematician, it is really essential to learn and understand the tensor and the matrix, because a lot of differential equations like Navier-Stokes includes tensor. So this one will be tau z b tau x z tau yz and the sigma zz. So for the z directions, we know that this one will be tau xz dy dz minus partial sigma zz plus partial sigma zz partial z bz dx dy. Alright, so we are done with writing the first, the matrix for the tensor. And we know that it's the same rule that applies. Since there's a negative sign, these all cancel out. Right? So they all cancel out. And we know that the dx dy zz, they'll become dv. So when we rewrite these equations on the right side, it will be df equals to, for the x direction, it will be for the y direction, sigma last but not least, and what do we have to do at the end? We need to multiply this by dv. So we know that the df dv, which we intend to find, will be, well, let me just copy and paste this part. Copy and paste. So the df dv will be this. But there is one more simplification that we gotta do, which is using the Newton's law of viscosity, we can rewrite these equations in terms of, so let's first write the Newton's law of viscosity. So Newton's law of viscosity states that the mu then let's say the random tau yx can be written as the mu times du dy. So the reason why we have du dy for the tau yx is because the plane that it's on is the variable that we need to derive this with respect to. And this x on the right side, which is the direction, is the velocity with respect to that direction. We know that the velocity in the x, y, and z can be written as u, v, and w. So this is the Newton's law of viscosity. So we can rewrite this df dv with using this Newton's law, where this becomes df dv equals to so we gotta rewrite all of these together. B partial x mu times partial u partial x plus partial y times mu times partial u partial y plus partial z There we go. So the explanation behind this is that we know that the direction, which is x, has to be rewritten as the u. And the plane is on, so the respective values, z and x, y. So the rewriting this differential equations for the rest, for the y and the z directions, it will be exactly like this. And when you took a higher order, the multivariable calculus, we know that there are very redundant repetitions in this matrix equation where the partial x's, y's, and the z derivatives, they repeat. For both directions. So technically speaking, this can be rewritten as like this. And people who took multivariable calculus will immediately recognize this as the Laplacian operator, right? So this can be rewritten as mu, because everything has mu, times the operator squared times, what do we have? U, V, W for all x, y, and z directions. So the velocity function. And here we go. We're done with deriving the force equation df dv for the viscosity functions, which is mu Laplacian velocity times all of them, the product. So we're done with the Navier-Stokes equation. We're rewriting all the equations. We know that this is the sum of the forces, which are rho g minus the pressure plus what we just found, this summation equals to ma, which is the Newton's second law, which also equals to rho times partial v partial t plus velocity times this velocity. Done. So here's the derivation of the Navier-Stokes equation, and we are completely done deriving QED. Thank you so much for watching this video, and if you have any questions, please leave the comments below. Thank you.